Unit 1, Chemical Energetics, Basic Aspects. Structure, Introduction, Expected Learning Outcomes, Chemical Thermodynamics and its importance, Thermodynamic Terminology, Thermodynamic System, State of a System, Extensive and Intensive Variables, Thermodynamic Processes, Work heat and heat capacity, reversible and irreversible processes, thermal equilibrium, the zeroth law of thermodynamics, summary, terminal questions, answers. Introduction. Energetics refers to the study of energy in terms of its flow and transformation within a system or between a system and its surroundings. The energy could be in the form of heat and radiation, work or some other means. Energetics is very broad field and its applicability in a given area can be qualified by putting a suitable prefix before it. For example, the term chemical energetics implies the study of flow and transformation of energy in chemical systems. Similarly, the term bioenergetics refers to the study of flow and transformation of energy in biological systems and so on and so forth. In this course, we are going to focus our attention on the flow and transformation of energy within chemical systems or between the chemical systems and their surroundings. We would begin the unit by defining thermodynamics and outlining its significance in chemistry. It would be followed by a definition and explanation of the terminology needed to understand and appreciate differentiate aspects of thermodynamics. Many of these terms may sound quite familiar to you, however, we would be defining them precisely in the context of thermodynamics. Having defined this, we would revisit the concept of heat, work and heat capacity. We would then explain the meaning of thermodynamic reversibility followed by the concept of thermal equilibrium. The understanding of thermal equilibrium would then be used to formulate the zeroth law of thermodynamics. In the next unit, we would take up the first law of thermodynamics, expected learning outcomes. After studying this unit, you should be able to define energetics, define chemical thermodynamics and outline its significance, explain different types of thermodynamic systems, explain the meaning of thermodynamic state of a system, define and differentiate between intensive and extensive variables giving examples, define different types of thermodynamic processes, explain the meaning of work and heat, discuss about their interconvertibility, define heat capacity, discuss its different types and state relationship between them, explain the concept of thermodynamic reversibility with the help of suitable examples, differentiate between thermodynamic reversibility and irreversibility, define thermal equilibrium and outline the requirements to achieve the same, and state and explain the zeroth law of thermodynamics. Thermodynamics is the only physical theory of a general nature of which I am convinced that it will never be overthrown. Albert Einstein, Lord Kelvin, William Thomson. Chemical thermodynamics and its importance. Thermodynamics is an experimental science based on certain generalization formulated on the basis of extensive observation of the microscopic world. Macroscopic means something that can be felt, seen or handled. Example, things that can be seen by naked eyes. This generalization are termed as the laws of thermodynamics and are applicable to all macroscopic systems, irrespective of then of their physical state, solid, liquid, gas, or any combination of these states. The term thermodynamics was coined by Lord Kelvin 1824 to 1907 to signify the dynamic nature of heat, which was then considered to be a kind of fluid. The term is based on two Greek roots with thermo meaning heat or temperature and durabikos meaning movement. If we take literal translation, thermodynamics means dynamics or motion of heat. We would be talking about the laws of thermodynamics and their significance in this course. Importance of thermodynamics. It is important to note that the thermodynamics is concerned only with macroscopic or large-scale properties of matter and make no assumption about the microscopic structure of matter. That is the structure of atom or molecules. It implies that the laws of thermodynamics are independent of the structure of atoms, which in turn means that even if the structure atom as we know today is modified, the laws of thermodynamics and their applicability will not change. In fact, the laws of thermodynamics were formulated mainly in the 19th century, well before the classical and quantum mechanical description of the structure of atom was understood. It is worthwhile to mention that there has not been even a single example that violates these laws. Another important aspect of thermodynamics is that it is an exact science and its laws can be expressed in terms of mathematical relationship. This allows us to derive mathematical equations that can describe and predict the outcome of many chemical and physical processes. This in turn allows us to apply these laws to practically all the branches of science and engineering. In the context of chemical system, the primary objectives of thermodynamics is to establish a criterion for determining the feasibility, means or spontaneity of a given physical or chemical transformation. Secondly, thermodynamics can help in determining the criteria and conditions for the equilibrium state for a spontaneous processes. The thermodynamic data can also be used to predict the direction in which the system would move to attain equilibrium and also provide the information about the extent of reaction for a given chemical reaction. It's time that we take up the terminology used in thermodynamics. You should pay attention to the terms being discussed, as you would be using them extensively in the course of your learning thermodynamics. It is therefore essential that you have proper understanding of these terms. Answer the following simple questions before moving ahead. Thermodynamics, like classical mechanics and classical electromagnetism, is an exact mathematical science. Each such science may be based on small finite numbers of premises or laws from which all the remaining laws of the sciences are deductible by purely logical reasoning. Guggenheim. SAQ1. What is the importance of thermodynamics in the context of chemical reactions? Comment this. Thermodynamic terminology. A number of terms are used in the study of thermodynamics and these have a specific meaning. Let us learn about some of the commonly used terms in the field of thermodynamics. Some of these may appear to be obvious or trivial, but we need to define and understand them so that there is no ambiguity in their uses. Thermodynamic system. A system in thermodynamics is defined as that part of the universe which is under consideration for the study. The system can be large or small, simple or complex. For example, a system could just be as small and simple as a beaker containing certain volume of distilled water or as large and complex as the ocean. A. B. A thermodynamic system can be of any size. A beaker containing certain volume of distilled water and B. An ocean. A thermodynamic system must have well-defined boundaries that may be real, fixed or movable or imaginary. A capable capped glass vial containing water or a reaction mixture Figure A has defined physical boundaries, whereas the ozone holes in the stratosphere layer of the Earth's atmosphere. B does not have real boundary, but it is also a thermodynamic system. Further, the boundaries of the system could be either fixed, example a fixed volume cylinder, and C are movable, example a cylinder fitted with movable position. D. A, B, C, D. The boundaries of thermodynamic system can be A real, B imaginary, C fixed, or D movable. In addition, the system may be homogeneous or heterogeneous. A homogeneous system is the one whose properties are uniform throughout the system. A beaker containing an aqueous solution of salt or sugar in water is a common example of homogeneous system. On the other hand, a heterogeneous system consists of two or more homogeneous systems that are separated by physical boundaries. A beaker containing ice in water is a common example of heterogeneous system. B. A. B. The thermodynamic system can be a homogeneous salt in water or heterogeneous ice in water. Surroundings. Theoretically speaking, the remaining other than the system part of the universe constitutes the surroundings of the system. The system and its surroundings put together constitute the universe. However, practically speaking, the surroundings are the part of the universe with which the system can interact. For the example given above, 1. The surrounding of the system of test tube containing distilled water are its immediate surroundings, the laboratory bench, the people around, or maybe the laboratory as a whole. 2. Similarly, for the ozone hole as a system, the surrounding may include the adjoining part of the stratosphere, the lower part of the mesosphere, the layer above the stratosphere, and the upper portion of the troposphere, the layer below the stratosphere. Types of system. A system is always separated from its surrounding by a boundary. The type of thermodynamic system depends on the characteristics of boundary. If the boundary of the system is such that it allows the transfer of matter and energy between the system and its surrounded through it, the system is classified as an open system. A glass test tube containing hot water is an example of an open system, as water can be removed or more water or some other kind of matter can be added to it, and also the temperature of water can be increased by heating it or decreased by allowing it to cool down by suitable transfer of energy. The system whose boundary does not permit the transfer of matter between the system and its surrounding but allows transfer of energy is called a closed system. If the glass test tube containing the hot water is suitably kept such that the matter exchange is not allowed, it would become a closed system. You may not hear that the energy exchange can still happen and the temperature of water in the tube can be increased or decreased. A closed system having a boundary that does not permit the transfer of heat to or from the surroundings is termed as an isolated system. In this case, neither the matter nor the energy can be exchanged with the surroundings. Types of thermodynamic systems. In open systems, both energy and matter can be exchanged with the surroundings. Closed system allows the exchange of energy only, whereas the isolated system does not allow exchange of either matter or energy. Open system, closed system, isolated system. Matter goes to energy. If the suitably capped glass test tube containing hot water is placed inside a thermos flask or in wrapped with a thick thermally insulating materials, it would become an insulated system. And then neither the matter nor energy exchange would be possible between the system and surrounding. Different types of thermodynamic system are schematically shown in figure. Hope you have understand the types of thermodynamic system. Attempt the following simple question to assess your understanding of the types of system. SAQ2 differentiate between open, closed, and isolated system with the help of suitable examples. Provide your own examples. Do not use examples given above. Comment this. The state of a system. The pressure P, volume V, and temperature T, and density P are example of some of the thermodynamics properties or thermodynamics variables of a system. These are used interchangeably. If we know the values of thermodynamics properties of the system, we say that the state of a system is defined or known. We have so far defined a thermodynamic system and its types. Let us raise a question. How do you characterize or describe a thermodynamic system? It is obvious that different systems have water in a test tube or the ozone hole would have a different description. One of the ways of characteristics or defining a thermodynamic system is in terms of its measurable physical properties like pressure, temperature, and volume, etc. That is, if we specify the physical properties of the system, we say that we have defined the state of the system. These properties are called thermodynamic properties or variable. The thermodynamic variables are also called state variables as these depend on the given state of the system and not on the past history of the system. Further, a state variable which depends on other variables is called a dependent variables, and the variables on which it is dependent are called independent variables. For example, if we have a simple sample of ideal gas taken in a cylinder fitted with a piston, then according to the ideal gas equation with PV equal to nRT, we can write V is equal to nRT by P. That is, the volume of the gas depends on the amount N, temperature T, and the pressure P. Here the volume is the dependent variable, whereas the amount of gas, pressure, and temperature are independent variables. On the other hand, if we wish to talk about the pressure of the gas in terms of other variable, then the pressure becomes dependent while NT and V become independent variables. In other words, we can say that the choice of independent and independent variables for the thermodynamics system is a matter of convenience. Extensive and intensive variables. Thermodynamic variables of a given system can be divided into two groups with intensive and extensive variables. An intensive variables is the one whose values is independent of the amount mass of the system, whereas the extensive variable dependent on the amount of the system. For example, temperature is an intensive variable. The temperature of a small chunk of ice broken from a slab of ice would be same as that of the slab. On the other hand, volume is an extensive variable. The volume of 10 moles means 1.8 kilograms of glucose would be more than that of 1.0 mole means 180 gram of glucose. It is important to note that the ratio of any two extensive variables is the intensive variables. For example, density, a ratio of two extensive variables with mass and volume is an intensive variable. The ratio of an extensive variable to the mass of system, that is property per unit mass, is called the specific property and is intensive. Example, specific volume. Similarly, the ratio of an extensive variable to the number of moles of the substances in the system, that is the property per mole, is called the molar property and is also intensive. Answer the following self-assessment question to gauge your learning about the intensive and extensive variables. All that is stated about intensive and extensive variables holds for a homogeneous systems as regards the heterogeneous systems consisting of number of phases. Some of the intensive variables may be different for different phases. SAQ3 categorize the following properties into extensive and intensive properties: volume, area, density, refractive index, temperature, dielectric constant, pressure, energy. Comment this. Thermodynamic processes. In our discussion so far, you have learned about thermodynamic system, their types and the variables that characterize the state of a given system. When a thermodynamic system undergoes a change in its state, we say a thermodynamic process has occurred. Suppose we take 150 gram of distilled water at 20 degrees Celsius in a beaker and heat it so that the temperature becomes 50 degrees Celsius. We have performed a thermodynamic process. In the course of a thermodynamic process, the system can undergo an exchange of matter and or energy with the surroundings. A thermodynamic process or a change in state is defined by clearly specifying the initial and final states of the system. The initial and final states in the example would be characterized as P 150 gram 20 degrees Celsius and P 150 gram 50 degrees Celsius respectively. Here P is the atmospheric pressure. As the beaker is uncovered, it is assumed that there is no loss of water due to evaporation. A thermodynamic process involves a change in at least one of the thermodynamic variables. Initial state P 150 gram 20 degrees Celsius, final states P 150 gram 50 degrees Celsius. You may note here that in the process described here, only one thermodynamic parameter, with the temperature, has undergone a change. Whereas other parameters like volume and pressure have not changed significantly. Thus, for a change of state or a thermodynamic process to occur, at least one of the thermodynamic variables must change. Can you think of any processes where none of the thermodynamic variables characterizing the state of the system undergoes a change? The answer is obvious. If none of the thermodynamic variables characterizing the state of the system undergoes a change, the state of the system remains unchanged, and it means that no process has occurred. However, sometimes it may so happen that the system undergoes a number of changes in state such that it comes back to its initial state with some characteristics. Such a process is referred to as a cyclic process. Different types of thermodynamic processes are given below. Some of these thermodynamic processes occur in such a way that one of the variables does not change, remains invariant. These processes are given special names and are used very often. You would learn about thermal equilibrium in section 1.5. You would learn about Bohm calorimeter in unit 3. One isothermal processes pronounced as isothermal, as is obvious from the name. It is a process in which the temperature of the system remains constant. For example, the conversion of 1 mole of ice into water as its melting point, 273.16 K 1 atm, is an example of the isothermal process. Isothermal processes are carried out in such a way that any heat flow into or out of the system occurs so slowly that the thermal equilibrium between the system and the surroundings is maintained. Two adiabatic processes, pronounced as adiabatic. It is a process in which no energy as it is allowed to enter or leave the system. Such a process occurs in systems that are thermally insulated and are accompanied by a change in the temperature of the system. Indicator diagram showing that PV graphs for different types of thermodynamic processes for a gaseous systems. Pressure P, volume V, isothermal, PV constant. Pressure P, volume V, adiabatic, PV to the power gamma, constant. Pressure P, volume V, P equal to constant, isobaric. Pressure P, volume V, isochronic. isochloric, V is equal to constant. In addition to the thermodynamic process given here, wherein some of the thermodynamic properties were allowed to change or remain constant, we have two more types of process which basically concern about the way the process is performed or allowed to occur. These are called reversible and irreversible processes. You would learn about this process in section 1.4. Three isobaric processes, pronounced as isobaric. Some things also called an isopastic processes. It is a process which is accompanied by no change in the pressure of the system, heating of water in an open vessel, or expansion of a gas in a cylinder fitted with a massless and frictionless piston are the example of isobaric processes. In both of these cases, the pressure is equal to the atmospheric pressure. For isochoric processes, pronounced isochoric, sometimes also called an isovolumetric processes. It is the process in which the volume of the system remains constant. Combustion of the substance in a bomb calorimeter about which you would learn in Unit 3 is an example of an isochoric process. This process for a gaseous system can be represented in terms of PV diagrams called indicator diagrams, figure 1.6. In order to move on, T or the laws of thermodynamics. We need to recall a few important concepts with work, heat, and heat capacity that you would have learned in your earlier classes. It is essential to clearly understand the definition of work and heat and the distinction between the two so as to understand the exchange of energy between a thermodynamic system and its surroundings. Solving the self-assessment question 4 would help you assess your understanding of thermodynamic state and processes. SAQ 4. What is the mean by the state of the thermodynamic system? Comment this. B. Can a cyclic process be a one-step process? Comment this. Work, heat, and heat capacity. We all do work and know it as any activity that requires muscular or mental effort. The muscular effort typically involves pulling, pushing, or lifting an object. In each of these, when we exert a force on a body such that the body moves from one place to another, that is gets displaced, we say work has been done. Greater the displacement, more the work. If, however, there is no displacement, there is no work. For example, suppose you start pushing a wall, there is no work irrespective of the force applied by you as the wall does not move. These examples on mechanical work can be used to give a definition for work. Let us see the consequences of applying force in the example given above. We find that the application of force causes an increase in the kinetic energy of the object. Thus, there is transfer of some kind of energy from the person to the object. This transfer of energy is called work. Therefore, we may define work to be transfer of energy via force. You may see in the figure given in the margin that a force F is applied on the block and it is moved by a distances. In this case, there has been a transfer of energy from the person to the object block. We say the work has been done on the block. Mathematically, the work can be given as the product of the magnitude of force F applied and the magnitude of displacement. S work Fs F. W is equal to Fs. There can be transfer of energy from the object also. Suppose an object is in motion and a person slows it down by applying force in a direction opposite to this motion. In such a case, the kinetic energy of the objects would decrease and an equivalent amount of energy will be transferred from the object to the person. We say that the object has been done work on the person. Such a work is called the negative work. Thus, we may define work as The energy transferred to or from an object by means of a force acting on the object, the work is said to be positive. If the energy is transferred to the object, its energy increases, and negative if the energy is transferred from the object, its energy decreases. Note: we should keep in mind that work is not a material substance that is physically transferred from the person to the object or vice versa. However, in thermodynamics, we get more specific and define work as a quantity of energy that flows across the boundary of a system by means of a force during a change in its state and is completely convertible into lifting of a mass in the surrounding. We should take note of two important aspects of this definition. First, work appears only at the boundary of the system, and second, it appears only during a change in the state of the system. The SI unit of work is joule, which is the product of a unit force 1 Newton acting through a unit distance 1 meter. 1 joule equal to 1 Newton meter. Here again, as in case of work, you have to keep in mind that heat also is not a substance or matter, it is just energy in transit. There is nothing as the amount of heat in a body. Though historically the heat was thought to be a substance and was called caloric. Around 1780, Benjamin Thompson, Count Ramford, demonstrated using boring of cannon barrels that the amount of heat was related to the amount of work done in the processes. This was later shown by Joule, 1840s. The heat-like work was energy, and the two were interconvertible. Heat. Let us now understand what is it. Heat is another type of energy in transit. Suppose we take two bodies at different temperature, hot to different extent, and bring them in thermal contact with each other. What would we observe? Our common sense tells us that there would be transfer of energy from the hotter object to the cooler one. For example, if we add 100 centimeter cube of water at 30 degrees Celsius to 100 centimeter cube of water at 60 degrees Celsius taken in a beaker, mix the two and monitor the temperature of the mixture, we will find that the temperature of the mixture become about 45 degrees Celsius and start decreasing gradually with time. The hot water has lost energy and the cold water has gained it, hence the temperature becomes about 45 degrees Celsius. Further, decreases is due to the loss of heat from the mixture to the surroundings, which are assumed to be at a lower temperature. Such an energy transfer that takes place because of a temperature difference is called heat flow or heat transfer, and energy so transferred is called heat and is symbolized as Q. In terms of thermodynamics, we may define heat as a form of energy that is exchanged at the boundary between a system and its surroundings by virtue of a difference in temperature between them, and flows from a point of higher to a point of lower temperature and causes change in the state of system. We should take note of two important aspects of this definition. First, that the heat appears only at the boundary of the system, and secondly, the heat appears only during a change in the state of the system. Since heat is also a form of energy in transit, so its SI unit is joule, J. Further, you should note that heat is an algebraic quantity having magnitude as well as sign. It is said to be positive energy. When energy is transferred to a system from its surroundings, we say that the heat is absorbed by the system. On the other hand, heat is said to be negative when the energy is transferred from a system to its surroundings. We say that heat is released or lost by the system. The heat capacity C of an object is the proportionality constant between the heat Q that the object absorbs or loses and the resulting temperature changes delta T of the object's heat capacity. Suppose we transfer a certain amount of heat Q to a system its temperature would increase by a certain value delta T, or for the temperature of the system to be increased by a certain value delta T, we must supply a quantity of heat equal to Q. The heat required is proportional to the change in temperature. Q equal to C of Tf minus Ti equal to C delta T, where Tf and Ti are final initial temperature of the system. The proportionally constant C is called heat capacity. Rearranging the equation, we get C equal to Q by delta T. For delta T equal to 1 degree Celsius, C is equal to K. The word capacity here is somewhat misleading, as it suggests that the system has some kind of capacity of holding heat or has heat. You must note that heat is not a material that is contained in an object, or the object has a capacity to hold heat. We can transfer any amount of heat to a system provided we have a body at temperature greater than the system. Thus, the heat capacity C of a given system is defined as the amount of energy as heat needed to raise the temperature of the system by 1 degree Celsius. Its unit are energy per degree or energy per Kelvin, that is joule per Kelvin, JK inverse, or joule per degree Celsius, J degree Celsius to the power minus 1. It is observed that the quantity of heat required to raise the temperature of a given mass of the substance by a certain value depends on its nature. For example, 4186 of heat energy is required to raise the temperature 1 kilogram of water by 1 degree Celsius, whereas to raise the temperature 1 kg of copper by 1 degree Celsius, we need only 387 joule of heat. Further, the transfer of heat to a system can be done under different conditions. If the transfer of heat is done under the condition of constant volume, the associated heat capacity is called as the heat capacity at constant volume, CV. And if the transfer of heat is done under the conditions of constant pressure, the associated heat capacity is called as the heat capacity at constant pressure, CP. Let us take two balls of copper having different masses. This would require different amounts of heat to raise the temperature by a certain value, say 1 K. That is, these would have different heat capacities. This sounds ambiguous that two balls of same material have different heat capacity. In fact, it is due to the difference in their masses. It is therefore convenient to define a quantity like heat capacity per unit mass, or specific heat capacity. See, the specific heat capacity would have the units of joule K inverse J inverse, or joule K inverse kilogram inverse, depending on the unit of mass. For 1 mole of the substances, the corresponding heat capacities are known as molar heat capacity as constant volume CVM and molar heat capacity at constant pressure CPM respectively. The units for molar heat capacities are joule K inverse, mole inverse. The specific heat capacity and molar heat capacity are intensive properties, whereas the heat capacity is an extensive property. Let us take an example to understand the difference between different types of heat capacity. The heat capacity per unit mass are called specific heat capacity, Cp and Cv. Cp equal to Cp by M. According to IUPAC, the adjective specific before the name of an extensive quantity is often used to mean divided by mass, and if the symbol for the extensive quantity is a capital letter, the symbol used for the specific quantity is often the corresponding lowercase letter. Example 1.1, 20.70 kilojoule of heat was supplied to 5.0 mole of water at 25 degrees Celsius, and the temperature of water increased to 80 degrees C. Calculate the heat capacity of the water sample, molar heat capacity and specific heat capacity of water. Solution. As per the equation, the heat capacity C is defined as C equal to Q by delta T. We are given Q equal to 20.70 kilojoule and delta T equal to TF minus TI equal to 80 minus 25 equal to 55 degrees C equal to 55 K. Substituting in the expression, we get the heat capacity of the water sample C equal to 20.70 into 1000 joule by 55 K equal to 376.36 joule K inverse. The molar heat capacity can be obtained by dividing the value obtained above by 5.0. The number of moles water in the sample, molar heat capacity C equal to 376.36 joule K inverse by 5.00 mole equal to 75.27 joule K inverse mole inverse. The specific heat capacity is the heat capacity per gram. It can be obtained by dividing the molar heat capacity by the molar mass. Specific heat capacity C 75.37 joule K inverse mole inverse by 18.00 gram mole inverse equal to 4.181 joule K inverse gram inverse. The values of Cp and Cv for a given solid or liquid systems are not much different. However, for gaseous systems, the difference in their values is significant, and for an ideal gas, it is given by the following expression: Cpm minus Cvm equal to R, where R is a gaseous constant. Further, the heat capacity depends on the temperature, implying that the amount of heat required to raise the temperature of a system by 1 K is different at different temperature. However, for small ranges of temperature, these do not change much and are usually taken as constant. We will talk more about the heat capacities and their temperature dependence in the unit 3. Solve the following questions before moving ahead. SAQ 5, 0.5 mole of an ideal gas is taken in a container at 298 K. By what amount? Give units also. Would its heat capacity at constant pressure be more than its heat capacity at constant volume? Comment this. Reversible and irreversible processes. The thermodynamics process can be performed in two different ways, reversibly or irreversibly. The thermodynamics reversibly and irreversibly is different from its reversibility and irreversibility that you have learned in the context of chemical reaction. In a reversible process, the change in the state of the system is made to happen slowly in an infinite number of infinitesimal steps. On the other hand, the same change can be achieved irreversibly in one or a few steps. Let us try to understand these terms with the help of an experiment. Let us take a thermodynamic system consisting of a certain amount an ideal gas taken in a cylinder fitted with frictionless and massless piston having an area of cross section of am square. A mass of 1 kilogram is placed on the piston and the whole system is placed in a thermostat in temperature T. Figure A. The gas occupies a volume V1 at an initial pressure equal to the atmospheric pressure and the pressure exerted by the mass on the piston. Let us call this pressure P1. The thermodynamic state of the system would be given as P1 V1T. Experimental design for understanding single-step irreversible expansion of a gas. A, B. am square, P1 V1T, P2 V2T. Let's now remove the 1 kilogram mass from the piston. The pressure reduces to be equal to the atmospheric pressure. Let's call it P2. The gas would expand to volume V2 against the opposing pressure P2 and produce a work W1. The new state of system would be P2 V2T. Figure B, work equal to W1 equal to minus P2 or P2 minus P1. This work W1 done by the system is generated in the surroundings. Let's move ahead and try to reverse the process by placing the 1 kilogram mass back on the piston. In this case, the gas would undergo compression under the influence of the opposing mass, or P1 of means 1 atm plus pressure due to 1 kilogram mass. The compression work would be work equal to W2 minus P or P V1 minus V2 equal to minus P1 of V1 minus V2. You may note here that the amount of work W1 generated in the surroundings during the expansion process and work 2 W2 that needs to be done by the surroundings to bring the system back to initial state are not equal. Let us compute the work in the cyclic process. State 1, state 2, state 1. W cyclic W1 plus W2 minus P2 of V2 minus V1 minus P1 of V1 minus V2 equal to minus P2 of V2 minus V1 plus P1 of V2 minus P1. W cyclic is equal to P2 minus V1 of P1 minus P2. As the terms in both the brackets of equation are positive, that therefore W cyclic is positive. When we analyze the system and the surroundings, we find that the system has come back to its original state, but the surroundings have not. The expansion process generated some work in the surroundings, but much more work was required to be done by the surroundings to get the system back to its original state. We say that some work has been destroyed in the surroundings in this cyclic process. Such a process is called an irreversible process. Let us again take the thermodynamic system consisting of same amount of the ideal gas taken in a cylinder fitted with frictionless and massless piston having an area of cross section of am square. Again, a total mass of 1 kilogram is placed on the piston, but in terms of 1000 masses of 1 gram each, and the whole system as before is placed in a thermostat at picture T, figure A. The gas would again occupy a volume V1 at an initial pressure equal to the atmospheric pressure plus the pressure exerted by the 1 kilogram mass on the piston. P1, that is P1. Experimental design for understanding reversible expansion of a gas. A, B, m square P1 V1 T, m square P1 minus dp B1 plus dv T. Now let's remove one of the 1 gram masses from the piston. The pressure would decreasing slightly, say by dp1, and the gas would undergo slight expansion by volume dv1 against the new pressure p1 minus dp1, figure B. This would generate a small amount of work dw in the surroundings. We allow the system to attain equilibrium and remove another 1 gram mass from the piston. Again the system expanded little and a work equal to dw2 is obtained in the surroundings. Again we let the system equilibrate. We continue the process of removing 1 gram mass, allowing the system to equilibrate. Remove the next 1 gram mass till all the 1 gram masses are removed one by one. At the end of process, that is when we remove the 1000th mass of 1 gram, the system would reach state 2, P2 V2T. That is the gas expand from a volume V1 to V2. Now we try to perform the reverse processes, that is we placed a 1 gram mass on the piston. The pressure would increase slightly and the gas would compress via a small volume. A work plus dw would be involved in this process. We allow the system to equilibrate and then put 1 gram mass on the piston. We repeat this process of placing 1 gram masses on the piston one by one every time, allowing the system to come to equilibrium. Once we place all the 1000 masses of 1 gram each on the piston, we find that the system has come back to state 1, P1 V1T. It is found that the total work obtained from the system in the process of expansion V1 to V2 and the total work required to be done on the system during a compression V2 to V1 are equal. In other words, no work is destroyed in the surroundings in the expansion contraction cycle. Such processes are called thermodynamically reversible process. If you think carefully, you may note that the work done during the second step of expansion process and work obtained during the 99th step, the contraction process would be equal. We have taken an example wherein the change from the state 1 P1 B1T to state 2 P2 B2T was achieved in say 1000 small steps. Such an approach is a reasonably good approximation to reversible process. Ideally speaking, for a process to be truly reversible, the change must be brought in an infinite number of infinitesimally small steps, which means it would need an infinite length of time to complete. Thus, we can say that the reversible processes are not real processes, these are ideal. We may approach the true reversible behavior but not achieve it. In other words, we can say that all real processes are irreversible. The process could be done in 1000, 10,000 steps using 100 milligram mass each time, or 1 lakh steps using 10 milligram mass each time, and so on. To make it even better, we could use 1 kilogram of sand and remove a grain of sand each time. FAQ 6 outlined the difference between the thermodynamically reversible and irreversible processes. Comment this. Thermal equilibrium, the zeroth law of thermodynamics. Temperature is a familiar property. We all seem to know it. However, it is quite difficult to define. We are also familiar with the fact that when a hot body and a cold body are brought into contact, the hot body becomes cooler and the cold body becomes warmer. The concept of warmer temperature is based on the qualitative idea of something being hot or cold as felt by us on the basis of our senses of touch. However, a measurement of temperature on the basis of sense of touch can be very vague, as our senses may deceive us and the outcome may be unreliable. For example, if we stand bare feet with one foot on dry grass and the other on the adjacent marble floor in open on a hot sunny day, the floor would appear much hotter than the grass even though the two may be at the same temperature. Similarly, a steel spoon may appear warmer than the wooden table on which it is kept. The difference is due to the fact that our skin measures the rate of energy transfer heat from the object rather than its temperature. Now suppose you ask anybody, how can you measure temperature? The immediate answer would be with the help of a thermometer. In other words, we all know the thermometer as a device to measure temperature. Have you ever thought, what is the basis of the device? The principle of thermometer is based on two things. Firstly, the concept of thermal equilibrium, and secondly, the fact that certain properties of material depend on temperature. Let us first understand the meaning and thermal equilibrium. Let us bring two closed systems into a thermal contact with each other and observe the changes in the properties of both the systems. You may ask, what are the systems and how do we observe changes? For this, let us assume that we have got two identical cubes made up of a novel material which changes its color with temperature. Let one of the cubes, system A, or be hot red colored and the other, system B, be cool blue colored, and we place these two in the two chambers separated by an insulated partition of an insulated box made up of a transparent material so that we can visually observe the color changes taking place inside the insulated box. Now when we remove the insulated partition, what would we observe? A schematic diagram of a thought of experiment described in the text, designed to demonstrate the directionality of heat flow. A, B. Insulated partition A, B. When two objects maintained at different temperatures are brought in thermal contact, they exchange heat with each other until they reach a state of thermal equilibrium, and after that, no further exchanges of energy takes place between them. We would observe that the colors of the two cubes changes gradually and eventually become the same, indicating the attainment of equality of temperature a state of equilibrium. Therefore, there is no further change in a color as there are no further exchange of energy between the systems. Such an equilibrium that is a consequence of temperature being the same is called thermal equilibrium. The heat flows from higher temperature to lower temperature and continues till the two objects attain same temperature. Now, if one of the objects happen to be a thermometer, the reading on the thermometer would change and become constant. This would indicate the temperature of the other objects. The thermal equilibrium is characterized by the equality of a single parameter. Temperature was first stated by a Scottish chemist and physician Joseph Black, 1728 to 1799. Let us extend our experiment and consider three systems ABC that are at different temperature initially. The arrangement of the three systems is given in figure. In the arrangement, we have separated system A and B by an insulating wall and have introduced thermally conducting slabs in such a way that this provides thermal contact between system A and system C and also between system B and system C. Thus, in our experiment, system C can interact thermally with system A and B, whereas system A and B cannot interact with each other. Having set the experiment, we observe the three systems from outside. Remember, our insulating box is made up of a transparent material that permits us to observe the system inside. What would we observe? A schematic diagram of a thought experiment described in the text to demonstrate the zeroth law of thermodynamics. Insulated partition A, B, C, A, B, C. The zeroth law is identical in form to a famous logical argument using deductive reasoning, viz. If alpha equal to beta, first premises, and beta equal to gamma, second premises, then alpha equal to gamma. Conclusion. Herein we arrive at a conclusion based on two proportion. In mathematical terms, the zeroth law of thermodynamics is said to be transitive. We would observe that the color of the three cubes representing the three systems change with time. After sufficient amount of time is passed, the three systems would be found to have same color, indicative of same temperature. Since there was a thermal contact between system A and system C, we expect them to be at thermal equilibrium. Similarly, the thermal contact between system B and system C also allowed for a thermal equilibrium to be achieved between them. The question comes up is that how do we explain the thermal equilibrium between system A and system B, as we did not allow any thermal interaction between the two. The observation, in fact, is the essence of the zeroth law of thermodynamics, which can be stated as if two thermodynamic systems A and B are in thermal equilibrium with a third thermodynamic system C, then the two thermodynamic systems A and B are also in thermal equilibrium with each other. The importance of this law was recognized only after the other laws of thermodynamics were formulated and is fundamental to them. Therefore, it is called the zeroth law. Summary. In this unit, we began by defining energetics as the study of energy in terms of its flow and transformation within a system or between a system and its surroundings. We highlighted its wide applicability and stated that in this course we are going to focus our attention on the flow and transformation of energy within chemical systems or between the chemical system and their surroundings. This was followed by introducing thermodynamics as a domain of science based on laws formulated by extensive observation of the macroscopic world. We defined thermodynamics as a branch of science that deals with the relationship between heat and other forms of energy and discussed the importance of thermodynamics in studying chemical reaction. Therefore, thereafter we took up the terms like system, its type, state of system, the thermodynamics, properties, etc., commonly used in study of this important scientific domain, and Explain them with the help of suitable example. This was followed by a brief discussion on thermodynamic process. Any change in state of a given system is termed as a thermodynamic process. Having defined the term used in thermodynamics, we revisited the concept of heat, work, and heat capacity, etc., and explain the sign convention for heat and work to be used in the context of thermodynamics. This was followed by a discussion on important concept of thermodynamics, reversibility and irreversibility. A thermodynamically reversible process is a process which is accomplished in an infinite number of infinitesimally small steps. Thereafter, we introduced the concept of thermal equilibrium and used the same to explain the way the thermometer works. The argument was extended to introduce the zeroth law of thermodynamics, whose significance was outlined. Terminal questions. Comment this.